we have proved this final similarity theorem, and that's best possible. To see why it's best possible, you could consider in this case, I mean, if your graph has a copy of complete graph on k plus 1 vertex, yeah, and yeah, so then it's impossible to even have a 칼라름 k vertices. And in order to see this is tight, you could consider the complete R-part-tight graph. With a slightly unbalanced one. So one has a bigger size. You have to make they are more vertices. Then even if the number of vertices here is divisible by R, there is no way that you can find the KR factor. Anyway, so the final similarity theorem determine the best possible minimum degree condition that guarantees a copy of KR. And what about for other graph? For other graph, can we find the minimum degree threshold for having that graph as a spanning subgraph? There is the following theorem by Sauer and Spencer, which provides the threshold for such problem. So let's say G and H are the n-vertex graph. And let's say the minimum degree of G is at least 1 minus 1 over 2 times the maximum degree of H times n minus 1. And we can show that the G contains H as a top graph. So we can prove this. So how do we prove it? Note that this condition says that if you take a maximum degree of H and then maximum degree of a complement of H, and that's smaller than n over 2. So what's this? This is n minus 1 minus this. Yeah, that's like roughly 1 over 2 delta H, and it's smaller than 1 over 2 delta H then. So you multiply, that's smaller than n over 2. So knowing that, let's show this. So assume n is at least 3, and we consider bijection of the vertices of H to vertices of G, which maps the both number of edges of H into edges of G. And let the vertices of B as x1 to xn, and vertices of G as b1 to bn. And assume that the pi maps xi to bi, for which I in here. Okay, and we call on he of H really bad. If pi is not in G, and good if pi is in G. So if the pi maps an edge of H into an edge of G, then it is good. Otherwise, it is bad. So If every edge is good, then we are happy. That means that this pi is an embedding over graph, so that you find the copy of H in G as a subgraph. Otherwise, assume that the x1, xn is in H, while b1, bn is not in H, not in G. And what we do is we will find K, which is between 2 and n minus 1, such that we can change the image of xk and xn of this I to obtain a better birejection. Say pi k, such that what pi k sends xk to bn and xn to bk, and rest of them it's same as pi. For each I which is not k or n. Then what? While doing that, we have to make sure that the we have to make sure that this does not introduce the new bad edge. So while doing this, we want to make sure that this does not introduce any bad edge. Give me a moment. And let's see, when do we get bad edge here? If, so we know that, let's say you have P1, Pn, so you have Pk. So let's say red are the edges of H, and black are edges in G. So this is a edge in H, but not edge in G, which is bad. And let's say if you have a Pj here, so if Pj a some day in one of the first n coordinate, we have that xj, xn is in edge of H. Let's say this is an edge. But after swapping, this is mapped to here, right? But this new one, say Bj, Bk is not an edge of G. So yeah, so okay, sorry. So if we swap these two, and how does it look? This and that. Then what? This one becomes yeah. Give me a moment. So yeah, sorry. Let's say let's control this first. So maybe it's better to draw it in a two graph. So this is x1, x2, x3, x1, xj, xk, and vn. You know that this is non-edge. Okay, so if this one is an edge, and if this one is non-edge, then what? If you map it here, then this edge maps to here, so which is a bad pair. So if you have these two conditions, then what? xj, xn is bad for pi k. And note that j could be 1. In that case, these two could be same. This maps to here, so that this one is not edge, then this is still bad, right? So we know this. And what's the other case? The other case is that for some, say, j in n-1, again, if we have this one is an edge, but this one is not an edge. And once you swap it, and this edge maps to here. So that's also bad. If we have xj, xk is an edge of H, and bj, bn is not an edge of G, then we could introduce a new bad edge, say Fj, Fk. And how many choices for such Jk? And how many choices for such Jk? For the first choice, what? You start from Bn, Xn, and then you choose J. There are delta H many choices for J. And for J, you have to choose Bk. There are delta non-edge of, you choose J which is not related to J, which is the maximum degree of complement of G many. And you have to subtract 1, which is the choice that J, K is same at 1, n. The 1n satisfies this, right? 1n satisfies this. So this many choices. And for the second one, again what? You start from Vn, you choose a non-edge, so this many choices for J, and then for this J, you have at most this many choices to K. And again, you have to subtract 1 for the case that this is 1, n. Again, 1, n is the legitimate one, so you have a neighbor J, and then non-neighbor in G, and then neighbor in H. So in total, so how many? So for each such, say, JK, we exclude K, as there are at most, what? 2 delta H delta G minus 2, which is what? This is more than n over 2, so this is more than n over 2. Such choices of JK other than 1, n, there exists K, which is not 1 and not n, which is not excluded. Then, then this pi k has no new bad edge. And the edge x1, xn is bad for pi, but good for this pi k due to our choice here. This is a contradiction to the choice of pi. So we choose pi as the ones that map the most number of edges of H into G. So this shows that this theorem holds. In fact, I mean, there is a conjecture regarding this, which is Borovach LDG and Catherine conjecture. And Borovach and Eldridge conjecture in 87, and then Catherine conjecture in 78, and then Catherine conjecture in 76. And it says that if the minimum degree of G is at least 1 minus 1 over maximum degree of H plus 1 instead of 2 times the maximum degree as in the previous theorem, then G contains H as a subgraph. Both, I mean, G and H are n vertices, have n vertices. So this is a conjecture, but it's still open. So you can kind of see that the minimum degree threshold for G depends on the maximum degree of H. But later we will see that we can do better. So this is for very general graph. So H and G are arbitrary graphs. And then later we will see that when H has low connectivity, then we can actually prove a better bound. Recall that in Heiner-Semeridi theorem, we have a KR factor, which is totally disconnected. So it has low connectivity. So we will see that that's the case covered by the theorem that I mentioned, the future result that we will talk about later for the graph with low connectivity. So we will discuss more in one of the one of the future lectures. Okay, thanks for listening. I'll see you in next video then.